Introduction to Teredo. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving into Teredo, which is a critical IPv6 transition technology that solves a very specific problem. When organizations started migrating to IPv6, they faced a significant challenge because most of the existing internet infrastructure still relied heavily on IPv4. Network Address Translation, or NAT, became a common solution to conserve IPv4 addresses, but it created an unexpected barrier for IPv6 adoption. Think about a typical home or office network. You have a router that performs NAT, translating private IPv4 addresses behind it to a single public IPv4 address. This works great for IPv4 traffic, but what happens when a device behind this NAT wants to communicate using IPv6? The NAT device doesn't understand IPv6 packets, so it simply drops them. This created a chicken and egg problem where people wanted to use IPv6 services but couldn't because their network infrastructure wasn't ready. Teredo was developed by Microsoft and standardized in RFC 4380 to address this exact situation. It is named after Teredo navalis, a type of shipworm that bores through wood. This is metaphorically appropriate because Teredo technology bores through NAT barriers to enable IPv6 connectivity. The technology provides automatic tunneling that allows IPv6 packets to traverse IPv4 networks and NAT devices without requiring any configuration changes on the NAT device itself. The beauty of Teredo is that it works transparently. A computer behind multiple layers of NAT can obtain a globally routable IPv6 address and communicate with native IPv6 hosts on the Internet. This made it possible for early adopters to start using IPv6 services even when their ISPs and network equipment did not yet support IPv6 natively. While Teredo has largely been superseded by native IPv6 support in modern networks, understanding it gives us valuable insights into transition mechanisms and how to solve complex networking challenges. How Teredo works. Teredo operates by encapsulating IPv6 packets inside IPv4 UDP datagrams. This is the fundamental mechanism that allows it to traverse NAT devices. Let me explain how this encapsulation works and why UDP was chosen specifically. When a Teredo client wants to send IPv6 traffic, it takes the complete IPv6 packet and wraps it inside a UDP datagram. The UDP header uses port 3544, which is the well-known port assigned to Teredo. The outer IPv4 header contains the IPv4 addresses that NAT devices understand, so the packet can traverse the IPv4 network successfully. From the NAT device's perspective, this is just normal UDP traffic, so it processes it like any other UDP packet, creating the necessary port mappings. The choice of UDP over TCP is crucial here. UDP is connectionless and stateless, which makes it ideal for tunneling because it adds minimal overhead and doesn't impose connection establishment requirements. Additionally, NAT devices handle UDP traffic in a predictable way, creating temporary port mappings in their translation tables. TCP would have introduced unnecessary complexity with its connection-oriented nature and would have made the tunneling less efficient. The Teredo architecture involves several key components working together. First, you have Teredo clients, which are the end-user devices that need IPv6 connectivity. These clients implement the Teredo protocol stack and can automatically configure themselves. Then you have Teredo servers, which are publicly accessible IPv4 hosts that help clients determine their NAT type and external IPv4 address. The servers also facilitate initial connection establishment. Teredo relays are another critical component. These are IPv6 routers that forward packets between Teredo clients and native IPv6 hosts. When a Teredo client wants to communicate with a native IPv6 address, the relay decapsulates the IPv6 packet from the UDP wrapper and forwards it to the destination. On the return path, the relay encapsulates the IPv6 response in UDP and sends it back to the client. Teredo address structure. The Teredo IPv6 address format is ingeniously designed to encode all the information needed for tunneling within the address itself. This self-contained approach eliminates the need for additional lookup mechanisms and makes routing decisions straightforward. Every Teredo address begins with the prefix 2001:0000, which is specifically allocated for Teredo use by IANA. This prefix immediately identifies the address as belonging to a Teredo client, allowing routers to make appropriate forwarding decisions. The prefix is 32 bits long, leaving 96 bits for encoding tunnel-specific information. Following the prefix, the next 32 bits contain the IPv4 address of the Teredo server that the client is using. This is stored in a straightforward manner without obfuscation. Knowing which Teredo server a client is using can be helpful for troubleshooting and for understanding the client's network topology. Different Teredo servers may be operated by different organizations, and this field makes that relationship explicit. The next 16 bits are reserved for flags that describe the NAT type and configuration. The most significant bit indicates whether the client is behind a cone NAT or not. Cone NAT is more permissive and allows incoming connections from any external host once an outbound connection has been established. Other bits in this field can indicate whether the NAT is port preserving or random, information that is crucial for establishing peer-to-peer connections. The most interesting part of the Teredo address is the final 48 bits, which encode the client's external IPv4 address and UDP port in an obfuscated form. The obfuscation is done using a simple XOR operation with all bits flipped. The external IPv4 address, which the NAT assigns to the client's traffic, is XORed with beginning with FF, ending with FF. Similarly, the external UDP port number is XORed with beginning with FF, ending with FF. This obfuscation serves a specific purpose. It prevents NAT devices that inspect packet payloads from incorrectly translating these embedded addresses, which would break the Teredo tunnel. Teredo client initialization. When a Teredo client first starts up, it goes through a carefully orchestrated initialization process to obtain its Teredo IPv6 address and establish connectivity. This process involves several steps that determine the NAT type and configure the tunnel parameters. The client begins by sending a router solicitation packet to a configured Teredo server. This initial packet is an IPv6 router solicitation, but it is encapsulated in a UDP datagram destined for the Teredo server's IPv4 address on port 3544. The client sends this from a randomly selected UDP source port, which will become its Teredo port. When this packet traverses the client's NAT device, the NAT creates a mapping between the internal private address and port and an external public address and port. The Teredo server receives this router solicitation and examines the outer IPv4 and UDP headers to determine the client's external IPv4 address and port. This is the address that the rest of the Internet sees for this client. The server then responds with a router advertisement packet, which is also encapsulated in UDP. This advertisement contains crucial information including the Teredo server's IPv4 address and the flags field that will be part of the client's Teredo address. Here's where NAT type detection becomes important. The server sends the router advertisement from a different IPv4 address and port than the client originally contacted. If the client receives this packet, it indicates that the NAT is a cone NAT, which is more permissive. Cone NAT allows incoming packets from any source once an outbound connection has been established. If the client doesn't receive this packet, the NAT is likely symmetric or restricted, requiring additional steps for traversal. Once the client receives the router advertisement, it has all the information needed to construct its Teredo IPv6 address. It combines the Teredo prefix, the server's IPv4 address, the appropriate flags, and the obfuscated external address and port. The client then configures this address on its network interface and can begin sending and receiving IPv6 traffic through the Teredo tunnel. The client also needs to send periodic router solicitation packets to maintain the NAT mapping, because NAT devices typically expire unused UDP mappings after a period of inactivity. NAT traversal mechanisms. Teredo employs sophisticated techniques to handle different types of NAT devices, each presenting unique challenges for establishing connectivity. Understanding these NAT types and how Teredo adapts to them is essential for grasping why Teredo works reliably across diverse network environments. Full cone NAT is the simplest and most permissive type. Once an internal host sends a packet to any external destination, the NAT creates a mapping that allows any external host to send packets back to that internal address and port. This makes Teredo connectivity straightforward because after the initial router solicitation, any Teredo peer or relay can send packets to the client. The client doesn't need to initiate contact with each peer separately. Restricted cone NAT adds a limitation where the NAT only allows incoming packets from external hosts that the internal host has previously communicated with. The external port doesn't matter, only the IP address. For Teredo, this means that before two clients can communicate, they may need to send packets to each other to establish the necessary NAT bindings. This is where the bubble packet mechanism becomes crucial. Port-restricted cone NAT is even more strict, requiring that incoming packets come from both a specific external IP address and port that the internal host has contacted. Symmetric NAT is the most restrictive type, where the NAT creates a different mapping for each destination the internal host contacts. This means the external port used for communication with the Teredo server might be different from the port used for communication with other peers, complicating direct peer-to-peer connectivity. Teredo handles these scenarios using bubble packets, which are special packets sent to punch holes through NATs. When two Teredo clients want to communicate, they first send bubble packets to each other. These are essentially empty UDP packets that create the necessary NAT mappings. The clients send these packets to the addresses they believe their peers are using based on their Teredo addresses. Even if the first few packets are dropped by the NAT, they create the outbound mapping that allows subsequent packets to flow. For symmetric NAT, where direct connectivity is impossible, Teredo falls back to relaying all traffic through a Teredo relay, which reduces efficiency but maintains connectivity. Communication flow. Let's walk through a complete communication scenario to see how all the Teredo components work together when a client wants to communicate with both native IPv6 hosts and other Teredo clients. Teredo handles these two fundamentally different scenarios in distinct ways. When a Teredo client wants to communicate with a native IPv6 host, the process involves a Teredo relay. The client creates an IP6 packet with its Teredo address as the source and the native IP6 address as the destination. This packet is encapsulated in a UDP datagram with the Teredo relay's IP4 address as the destination. The client determines which relay to use through DNS or anycast mechanisms. The relay receives the UDP packet, extracts the IP6 packet, and forwards it into the native IP6 internet. The relay maintains state about this connection so it can forward return traffic back to the client. When the native IPv6 host responds, its packet is routed through the IPv6 internet to a Teredo relay, which might be the same relay or a different one depending on routing. The relay recognizes the destination as a Teredo address because of the 2001:0000 prefix. It decodes the embedded IPv4 address and port from the Teredo address, encapsulates the IPv6 packet in UDP, and sends it to the client's external IPv4 address and port. The NAT device forwards this to the client because the outbound connection has already created the necessary mapping. Communication between two Teredo clients is more efficient because it can happen directly without relays in many cases. When a Teredo client wants to reach another Teredo client, it decodes the destination Teredo address to extract the target's IPv4 address, UDP port, and Teredo server. Before sending actual data, the client sends bubble packets to establish NAT traversal. These packets create the necessary NAT bindings on both sides. After the bubble packets succeed in opening the NAT, the client can send IPv6 packets directly to the other client. Each IPv6 packet is encapsulated in UDP with the outer IPv4 headers pointing to the peer's external address and port. The NAT devices on both sides forward these packets because the bubble packets already created the necessary mappings. This direct peer-to-peer communication is much more efficient than routing through relays. However, if direct communication fails due to symmetric NAT or firewall restrictions, Teredo falls back to using a relay as an intermediary, introducing additional latency but maintaining connectivity. Security considerations. Teredo introduces several security considerations that network administrators must understand and address. While it enables IPv6 connectivity, it also creates potential security vulnerabilities that can bypass traditional perimeter defenses. One of the primary concerns with Teredo is that it can bypass firewall policies. Many organizations have carefully configured their firewalls to control IPv4 traffic, but Teredo traffic appears as ordinary UDP packets to these firewalls. The firewall sees UDP port 3544 traffic and may allow it through, not realizing that IPv6 packets are being tunneled inside. This means that the firewall's IPv4 rules are being circumvented, and IPv6 traffic can flow in and out of the network without going through the intended security controls. The automatic nature of Teredo exacerbates this issue. Windows operating systems have Teredo enabled by default in many versions, which means that employees' computers might be establishing Teredo tunnels without the IT department's knowledge. These tunnels could be used to exfiltrate data or provide external access to internal systems, completely bypassing the organization's firewall. This is why many enterprise networks explicitly block Teredo or disable it on client machines through group policy. Spoofing and man-in-the-middle attacks are another concern. Because Teredo uses UDP, an attacker could potentially inject malicious packets or intercept traffic. The protocol includes some protections against this, such as the nonce exchange during router solicitation to prevent simple spoofing attacks. However, these protections aren't as robust as authenticated key exchange protocols. An attacker who can observe traffic between a client and server might be able to inject packets or manipulate the connection. Authentication in Teredo is minimal by design to keep the protocol lightweight and compatible with diverse network environments. There is no built-in encryption or strong authentication of Teredo servers or relays. This means you are trusting that the Teredo infrastructure components are legitimate and not malicious. In enterprise environments, it is recommended to either use trusted Teredo servers or disable Teredo entirely in favor of more secure IPv6 transition mechanisms. Some organizations deploy their own Teredo servers and configure clients to use only those servers, maintaining better control over the infrastructure. Teredo configuration. Configuring Teredo varies depending on the operating system, but Windows provides the most comprehensive built-in support since Microsoft developed the technology. Let's explore how to configure, enable, disable, and troubleshoot Teredo on Windows systems. On Windows, the netsh command line tool provides complete control over Teredo settings. The interface IPv6 set Teredo command allows you to configure the Teredo state. The most common states are default, client, disabled, and enterprise client. The default state enables Teredo when no native IPv6 connectivity is available and the system is not on a managed network. The client state forces Teredo to be enabled regardless of other connectivity. The disabled state completely turns off Teredo functionality, which is often used in enterprise environments. The enterprise client state is specifically designed for corporate networks where you want Teredo available, but with restrictions on which servers can be used. When you set the state to client or enterprise client, you can also specify which Teredo server the client should use. The server name parameter in the netsh command accepts either a DNS name or an IPv4 address of a Teredo server. By default, Windows uses Microsoft's public Teredo servers, but organizations can deploy their own servers for better control and security. Setting a specific server name ensures that all Teredo traffic goes through infrastructure you trust. Viewing the current Teredo configuration is done using the netsh interface IP6 show Teredo command. This displays comprehensive information including the current state, the server name being used, the client's Teredo IP6 address if one has been obtained, the NAT type that was detected, and whether the client is currently qualified to use Teredo. This command is invaluable for troubleshooting connectivity issues. Testing Teredo connectivity can be done in several ways. You can use the ping command with an IPv6 address to verify that IPv6 connectivity is working. Specifically, pinging a known Teredo address or a native IPv6 address tests different aspects of the tunnel. The netsh interface IPv6 show route command displays the routing table and should show a route for the 2001:0000 prefix pointing to the Teredo interface. Additionally, you can use traversal with an IPv6 destination to see the path packets take through the Teredo tunnel. Alternatives to Teredo. While Teredo solved an important problem during the IPv6 transition, several alternative mechanisms have been developed that address similar challenges, often with better performance or security characteristics. Understanding these alternatives helps in choosing the right solution for specific scenarios. 6-to-4 is another tunneling mechanism that encapsulates IPv6 packets in IPv4, but it works differently from Teredo. Instead of using UDP, 6-to-4 uses Protocol 41, which is a dedicated IPv4 protocol number for IPv6 encapsulation. The advantage is that there is no UDP overhead, making it more efficient. However, 6-to-4 has a significant limitation. It does not work through NAT devices. The tunnel endpoints must have public IPv4 addresses. This makes 6-to-4 suitable for connecting IPv6 networks across IPv4 infrastructure, but not for individual clients behind NAT like Teredo addresses. ISATAP, which stands for Intra-Site Automatic Tunnel Addressing Protocol, is designed for enterprise networks rather than internet-wide connectivity. It allows IPv6 packets to travel between nodes within a site that has IPv4 infrastructure. ISATAP uses Protocol 41 like 6-to-4, and it can work in environments where there is no native IPv6 routing. The key difference from Teredo is that ISATAP is designed for controlled enterprise environments where you have administrative control over the infrastructure, rather than for traversing unknown NAT devices on the public internet. 6RD, or IPv6 Rapid Deployment, is a mechanism developed by ISPs to quickly provide IPv6 connectivity to customers while still using their existing IPv4 infrastructure. It is conceptually similar to 6-to-4 but with provider-specific addressing and configuration. ISPs deploy 6RD border relays that handle the encapsulation and decapsulation. The advantage over Teredo is that it is operated and controlled by the ISP, providing better performance and reliability. However, it requires ISP support, unlike Teredo, which can work without any ISP involvement. Native IPv6 with dual stack is the ultimate goal and the best solution when available. Dual stack means the network fully supports both IPv4 and IPv6 simultaneously, with no tunneling required. Modern ISPs increasingly provide native IPv6 connectivity, making tunneling mechanisms like Teredo unnecessary. The performance is better because there is no encapsulation overhead, and security is improved because you are using the network's intended protocols rather than tunneling around them. As IPv6 adoption continues to grow, tunneling mechanisms are gradually being deprecated in favor of native connectivity. Practical applications in future. Understanding where Teredo has been used in practice and its current relevance helps contextualize the technology and informs decisions about whether to use it in modern networks. Historically, Teredo was most commonly used on Windows client machines where users needed to access IPv6 only resources, but their ISP or network did not provide native IPv6 connectivity. Gaming consoles and peer-to-peer applications also used Teredo to establish direct IPv6 connections between clients, taking advantage of the NAT traversal capabilities. Skype, for example, used Teredo in some of its peer-to-peer connectivity scenarios to improve call quality by establishing direct connections when possible. However, the use of Teredo has declined significantly as native IPv6 deployment has expanded. Major ISPs now provide IPv6 connectivity to most of their customers, either through dual-stack or IPv6-only networks with NAT64 for IPv4 compatibility. Enterprise networks have also been upgrading their infrastructure to support IPv6 natively, eliminating the need for tunneling mechanisms. Modern operating systems still include Teredo for backward compatibility, but it is often disabled by default or configured to only activate when absolutely necessary. From a security perspective, many organizations actively block or disable Teredo in their networks. The security concerns we discussed earlier, particularly the ability to bypass firewall policies, make Teredo unsuitable for many enterprise environments. Network security policies increasingly mandate that all traffic should pass through centralized security controls, and Teredo's automatic tunneling bypasses these controls. For organizations that need IP6 connectivity before their infrastructure is ready, more controlled alternatives like configured VPN tunnels or ISP-provided 6RD are preferred. Looking forward, Teredo is considered a legacy technology. New deployments should focus on native IPv6 connectivity rather than relying on transition mechanisms. However, understanding Teredo remains valuable for several reasons. First, you may encounter it in existing networks that haven't fully transitioned to IPv6. Second, the concepts behind Teredo, particularly NAT traversal and encapsulation techniques, are applicable to other networking technologies. Third, it provides insight into the challenges of transitioning between network protocol versions, lessons that may be relevant in future technology migrations. Thank you for your attendance. Please consider subscribing to the channel.